Okay, so we found A0 and A1, and that was an amazing triumph. Let's continue with that. I'm going to take this guy right here and copy it. And I'm going to see what we can do about this to figure out the other ones. I'm going to copy this. I'm running out of room here. I'm going to add another page if you don't mind. I'll paste it here because I'm going to have a lot more room here. So we found that. Now, how do we figure out, well, A2? That's what I want to figure out next. We do another brilliant idea. We take this one we already knew, and we slap a derivative on both sides with respect to x. By the way, this goes on forever. Don't think it stops here. We take the derivative on both sides. What's the derivative of cosine? The derivative of cosine is, of course, negative sine of x. And what's the derivative on the right hand side? This part goes to 0, which I wanted to kill this one, and that will just leave a 2a2 there so beautifully with no x's. And then I'll have a 3 times a 2 times an a3 times an x, and then I'll have a 4 times a 3 times an a4 times x squared. What I'm doing here is taking the derivative of this, the derivative of this, the derivative of this, the derivative of this is 0, and so on and so forth. I'll just write one more for fun. That would be a 5 times a 4 times an a5 times an x to the third plus dot 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 dot. Okay, and then I do something so amazing. I substitute and I ask the question, what if x is equal to 0? That will kill this one. It will kill all this because they all have zeros, and it'll leave me with a statement that says that negative sine of 0 is equal to 2a2 plus 0. And of course, sine of 0 is equal to 0, so this tells me that a2 is equal to 0. Boom. Notice I already have 3 of them. I'm going to keep track here. A naught we said was equal to 1. Sorry. 0, A1 was equal to 1. A2 is equal to 0. Now we need A3. Now you're getting the hang of it. To find A3, I'm going to take this one right here and take the derivative of it. Because if I take the derivative of it, some nice things will happen on the right-hand side. On the left-hand side, I've got the sine of x. The derivative of that, of course, is cosine of x. On the right-hand side, this part vanishes. X times the constant will just be the constant. So all I get is 3 times 2 times a to the third. Plus 4 times 3 times 2 times a4 times x plus 5 times 4 times 3 times a5 times x squared. And so on and so forth. And so I get that, and of course I'm going to plug in x equals 0. By plugging in x equals 0, I ask myself, if x equals 0, what do I get? If x equals 0, I get that negative cosine of 0 is equal to 3 times 2 times a3, plus, of course, all that's going to vanish, so it's plus 0. So I can solve for a3. a3 is equal to negative 1 divided by 3 factorial. So a3 is equal to negative 1 divided by 3 factorial. And after a while, you'll see the pattern here. The pattern is quite easy. I could keep going forever, but I'll let you do that. Pause the video and do that. Let me erase this so I can show you the pattern. I'll just use dot, 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 dot here. A4 is going to be equal to 0. A5 is going to be equal to 1 over 5 factorial. A6 is going to be equal to 0. A7 is going to be equal to negative 1 over 7 factorial, and so on and so forth. And in doing this, boom, I've got the exact DNA for sine of x. We set out saying that sine of x, we had the wishful thinking that we could write it as a polynomial as a naught plus a1x plus a2x squared plus a3x to the third. This unthinkable absurdity, right? Sine is a polynomial, and in fact, we're getting some success here. We're actually solving all of the coefficients, and so this becomes, look at all the even ones vanish. That one vanishes, that one vanishes. So this is 0, 0, 0. All the even ones vanish clearly because sine is an odd function. Duh. So only the odd ones survive, and they survive as such. Sine of x is equal to x. I'm putting that 1 there is going here. So it's 1 times x. 1 times x. That goes there. That just gives you x. The a2 is 0. The a3 is negative 1 over 3 factorial. So this will be minus 1 over 3 factorial x to the third plus 1 over 5 factorial x to the 5 minus 1 over 7 factorial x to the 7th plus 1 over 9 factorial x to the 9th minus 1 over 11 factorial x to the 11th, dot, 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 dot. Yippee-ki-yay. This, my friends, is the first non-trivial example of us converting a function into an effing polynomial. It's incredible. Now, you can go home and program a calculator yourself. All this is addition and subtraction, and multiplication. That's why they pay me to explain this kind of stuff. All right, so beautiful. I think I should pause here. The next thing I want to do is take this to the next level. I did it for sine. I want to do it for a generic function. I want to be so generic that I could do it for any function where this can be done, and it can't always be done, but if it could, a0 plus a1x plus a2x squared. I want to go around and be so powerful and so cocky that I could turn any function into a polynomial. Well, that's kind of a lie, but any function that could be turned it, I want to know how to do it. That would be the next thing. So in other words, we would have some formulas for all these coefficients. We would generate some templates, and then we could just apply it. And we will have done it not just for sine, but all functions where this is doable. All right, that will be next. Let me pause this. This is too good to lose, and then we'll continue.